Now we'll discuss some examples of in situ bioprinting approaches or strategies. So as I have mentioned earlier, that handheld bioprinter or bioprinting tool can be developed, and that can be used to, like a conventional bioprinting method, that can be used to deposit or write structures directly on the patient's own bed. So one such there are some examples where researchers have already developed handheld bioprinting tools, like a Co-Axial bioprinting tools here. So a handheld by in this. So please refer to this literature where they explain in great detail about the designing of this bioprinting tool, and also about the application of this bioprinting method for cartilage tissue regeneration. So here, what they have done here is they have fabricated a handheld biofabrication tool, so that can be, and they have also named it biopen, because this is used for writing as kind of writing. We can use this handheld device to bioprint structures. So this enables the deposition of living cells and biomaterials in a manual, direct write fashion. So here, the biopen, is kind of a device that can be easily handheld, and then it can be used for depositing cells and biomaterials directly on the wound bed manually. That means surgeons can control the device, and then they can deposit the living cells along with biomaterials on the wound bed. And if you see, uh, they have actually, in this particular work, they have used again gelma and hyaluronic acid methacrylate, as I have already mentioned earlier. This gelma plus HAMA, this hydrogel they have used for bioprinting of these typical structures, and then they have also used UV cross-linking to cross-link the printed structures directly on the patient bed. So here, this is the bioing that have been they have been used this they have used this for their applications. Now uh, bio this biopen, this has custom titanium nozzles, so that's why that way that can use for multiple ink formulation in a collinear geometry side by side. So basically this biopen has two compartments. In the next slide I will show you the images of this thing. But this bioink has two compartments, where the core cell, coaxial, that's why core and cell, as I have already discussed earlier, that there is a core compartment that is in the middle, in the center, and there is a shell compartment that is surrounding that core area. So through these two compartments can be two different types of materials can be fed through these two, or can be fed through this two compartments, and then they can have a core shell, or a concentric or coaxial uh, strand or line can be formed, and that can be used for fabricating different types of structures. So they have used two collinear titanium nozzles. They have fabricated specially for, so that multiple ink formulation can be bioprinted using this device. And also, the because this biopen, again, this biopen is connected to a pneumatic pressure mechanism. That means the pneumatic pressure can be applied on this piping for extruding the piping through the nozzle. Now here, as it has two different compartments, one core and shell, so two that those two compartments can be separately pressurized, and so different pressures can be applied to these two compartments, and that can be controlled further. So that's why this system, the pneumatic system, independently applied extrusion pressure for both chambers allows geometric control of the printed structures and for creation of compositional gradients. Suppose we can, or they have shown this, that they can control the extrusion of these two compartments separately. That means, suppose when they want to extrude more core material and less cell material, and also vice versa, that can be easily done. So they are, that's why they can create any type of anatomical structures. That means any printed structures, they can control the geometry of the printed structure, also the compositional gradient. So there we can vary the composition. Suppose we want more cell, more core material, more cell material, more less core material, more cell material. So this kind of combinations can be very well be done with this kind of, because it has a because it's a two chamber nozzle, and those two chambers can be separately connected to pneumatic extrusion based pneumatic mechanisms. And this, because this they can control independently, so that pneumatic system control extrusion of these bioing chambers independently. Because they are present left right, but when they come out, that time in the nozzle there is a coaxial geometry. So now when the extrusion is activated, extrusion can be activated by these 2 foot pedals connected to pressure regulators. Like, so now surgeons, when they, like, suppose their hand is busy with the, because they are handheld this device and they are doing this, they are kind of writing or depositing the cylinder structure. Now how can they control the extrusion of this material? That is there, the pedals, foot pedals are used. So by this foot pedal they can control the pneumatic thing. So the pneumatic actuator, suppose there's an actuator that can control the pneumatic mechanism. So by foot pedal they can switch it off and on. So whenever they are, suppose they are using that handle device to extrude material, they can, with the foot, they can, so foot, with the foot they activates, they can activate the pneumatic mechanism, pneumatic pressure mechanism, and by this way they can control the deposition. And then again the UV curing system is also activated via the third foot pedal, so that in the same handheld device they have a UV light generating mechanism by which they can switch that. Suppose they printed and then they want to switch to E1, there is a third pedal for that. That third foot pedal is available by which they can activate the light. So here more controlling of the bioink is possible because of the presence of all these different mechanisms. So by this way they can ability to directly control the deposition of regenerative scaffolds without presence of cells, live cells, during the surgical process, and that presents an exciting advance not only in the field of cartilage or bone regeneration but also in other fields. Because in this paper they have mostly concentrated on cartilage tissue regeneration with this kind of handheld device, but this can also be used for different different types of tissue engineering. So this is the advantage of a handheld coaxial bioprinting method. Now let's just see their the images of this thing and also the a few results from this particular study. So what they have done, so this is the image of this particular handheld device, where you can see here this is the cross section where two different feeding mechanisms, like this for the shell, for the coal, two different feeding mechanisms possible, and then that can be pneumatically activated, and then in the nozzle they are coming in a concentric manner like here, and then the core and shell material is coming out separately, and then they are making the whole structure a concentric strand like structures. Now here this device, as you see, when this is the further, this is the device when the, suppose when the bioinks are filled into these two chambers, and then that is the when it is on, or it is the pressure is on, then the core material you see and the cell material is coming out. Now we can, if we control the extrusion rate of these two materials, then actually we can, by this way we can control the amount of material coming out through the core, nozzle and the cell material, and there we can control the volume of these two. Suppose proportionally we can increase the core material percentage over the whole thing, and also cell material percentage also can be controlled further, and by this way we can make this kind of structure. Now suppose they have printed this structure like this, where the core material is, suppose green fluorescence is used for to denote to identify the core material and the shell is red fluorescence is used to identify the shell material. You can see here the how the structure look like when the printed like this. So core is present in the center and the cell is present in the outer periphery. So this is about the biopen, the structure of the biopen and how does it work. Then they have done a series of study to first to evaluate the different like cellular responses on this kind of bioprinting techniques. Like the cell viability is one such thing that that is the very first thing mostly for any type of bioprinting. There the cell viability is the very first thing that has to be evaluated, because after printing, suppose if the cells are not viable within the construct, then that construct is of no use, not useful. So that's why bioprint cell viability is the major or the most important and very fast evaluation method to be employed. So in this case, they have used two different dyes for identifying the or evaluating the live cells present in core as well in shell. So we can in the shell. So you can see here this thing in the through Co-Axial they have printed this thing, and then this green channel is for the core and the shell is also given another like this kind this struck color this sand color. So here this is the two different channels are seen are shown like this, how the core material is coming out, how the shell life cell material is coming, cell and core material is coming out, and then the merged you can clearly see that the core cells present that core cells present in the core material is present in the center of the structure. But in case of monoaxial, also the same thing. And monoaxial, where both these things can get mixed together. Here you see, like the live cells and monoaxial, like the some this thing and this thing, both the things can get merged, and that can be easily visualized here, like with the live cells. Now here, another interesting thing. This graph also shows the quantification of this the live cells. That is from this graph, from this sorry from this image, they have quantified the viable almost close to 90, more than 90 or close to 100% cell viability is present in both case thing, both in both this core shell and also in the monoaxial dotted printed samples. So the cell viability is well maintained, that we can clearly see here. From here the cell viability is well maintained and more than 90% cells are viable, and that's a very good indication for bioprinting. Then also the next thing they have seen, suppose they have printed both core and cell separately, and now what will happen, what is happening if we culture them for some time, then what will happen to this? Now if you can clearly see here at the beginning, day one, almost like almost 20% or 20 around 30% of core cell percentage was there, cells were present in the core, almost like that is 30% of the overall volume, and 70% in the cells are present. But upon culturing at 15 days, that is the core cell percentage is getting higher, and the core means the cells present in the core, their volume is getting, their number is getting increased, and the shell, their number is almost. So overall, there is a change in this, means there is a change in the percentage of the cellular distribution within the construct, that is also getting changed, and that is the outcome of this study. And here it can be clearly seen this in this from this image also it can be clearly seen that the cells that is present in the core, their number is increased, and then the whole how the whole construct looks like. Also they have seen the a cryosection, they have done a cryosection of this construct, and then they've seen the 10 micrometer cryosection, they have this, they are also clearly seen this is the core area, and that is the cell area, right, at 7 days. The core area is less than 7 this thing, but at 15 days the core area is getting increased and the cell area is getting reduced. You can clearly see here the cells present in the core area, that is getting increased, and the cell area that is getting reduced. So this is another important observation from this study. Though we can maintain different cellular percentage at different locations, but for some reasons the cells present in the core, that is they're proliferating much faster than the cells. Another important observation from this study is that due to the core cell bioprinting, like coaxial bioprinting, with this device, the structural integrity of the cell-laden hydrogel is much better than the only monocell culture, monocell bioprinting. Because here what happens, this core shell actually that facilitates proper gelation and also proper positioning of the cells, and also we can clearly see look how good the structural fidelity when we actually print with this kind of structure, with this thing, right? Like this is the first, suppose this is the first layer where these are the live cells. There's a cell number is very high here. The cells are this structure is, this line is printed. On top of that, the another line is printed, and they are also the see the cell viability is maintained. Yeah, here they have again shown the like where the cell and where the core is present. Now here see the core is cell is present here, and the core is also present here. So both these things are present here, present, and because of the presence of both this core and cell material, this structures can get cross-linked faster, and the structural integrity can be very well maintained. So this is another major advantage of this study. And let us see a few more examples on this in situ bioprinting methods. Like here, in this particular study published in this journal, here you can clearly see that they have used a robotic assisted biological laser printing method for a critical size bone defects with nano hydroxyapatite printing. So what they have done here, they have used a high throughput biological laser printing methods, and they have used a mice calvaria bone that is typically present on the skull. So that skull bone there, and then they have created a 4 mm diameter defect with trephine blade. A 4 mm diameter defect was created on the mouse calvaria bone, and that because they've opened the skin part and the skin flap from the skull, from the head part, and then the bone was exposed, calvaria bone, and then bone was a cut was given, like a 4 mm diameter cut was there. And that defect, wound defect, now their interest is to print a bone scaffold on that bone defect. Then they have used nanohydroxyapatite with this laser assisted bioprinting technique, as we have discussed earlier. In the laser assisted bioprinting, suppose with the biowing, when you coat this, or a nano hydroxyapatite slurry was coated, and then that was used as biowing, and then they have done this laser assisted bioprinting. So they have directly printed the nanohydroxide on the calvaria defect model. Then they have assessed that defect area by printed structures, and they found that this kind of bioprinting can be used to treat this kind of bony defects. So this study, though very preliminary, but this study has clearly demonstrated that in vivo bioprinting using laser assisted technology can be very well used for bioprinting of this kind of structures. Now let us discuss another very important study where they have used, this is in situ bioprinting of autologous skin cells. Now this study was done in Wake Forest Institute of Regenerative Medicine, where they have used a inkjet bioprinting based systems for deposits for the printing cells. Like here, what they have done here, a 260 micrometer nozzles are there, and their 8 nozzles are connected to this print head, and then that can be used for printing structures. So a very small area, these nozzles are connected to a very small printed, so that can be very well be used within this surgical room. Like this is the schematic where the patient can be lie down on the this bed, and then the bioprinter can be used to print the cell structure directly on the bed. So this is there's some more examples, few more things. They have also have another very interesting thing. They have used a scanner, that is Jet Scan 700. So that scanner they have used to scan the wound. So that by this way, the wound can be very well scanned, and then that can be used to generate that the wound volume, defect volume. Like this case, in this case, as you can see the schematic in the C, here it is clearly seen that this laser is actually scanning the wound surface. Like this is, suppose this is the wound present on the in the skin page. Like this is the defect. Then this scanner scanning the wound bed like this. Then it actually calculates the volume of the defect. And then as we know, skin is mostly, it is the, like suppose the dermis and then the epidermis. Then what it does, it calculates how much amount of dermis and how much amount of epidermis is damaged, and that much amount, suppose first that much amount of dermis, and then the same amount, other amount of the required amount of epidermis can be put back into those patients or into that defect area on defect area. So this process, so using this laser scanner, they have they have used to actually instant to get the volume of the wound area instantaneously. They have used this laser. Another important thing is, after scanning this laser, that volume is actually then again it is being converted into a CAD file, and from that CAD file the bioprinter, now bioprinter can, the command can be given to the bioprinter by to print the required amount of dermis and epidermis. So this technology is very powerful to actually to identify and also calculate or estimate the wound volume, and then subsequently bioprinting the structures. Now here, this is the example how this whole process works. Now suppose they have used a model to create this kind of skin wound, like this is a skin wound. Now this laser is scanning the surface, right? And then the CAD model is generated based on this scanning thing, and where this CAD model is can be here, where accurately the dermis and epidermal part can be generated, and then you see there this is the thing, how much about dermis and epidermis can be there. This part is getting created, and then the bioprint head actually depositing the first the fibroblast tissue, first the fibroblast cells within the thing, and then the keratinocytes on top of that. Now this whole process, like from the scanning to this thing, is mostly it is automated. So this thing, very less user intervention is required for printing this kind of structures. Printing a customized, like printing a in situ bioprinting of structure directly on the wound bed. Right? This is the thing. Now here, then they have done this. Also, they have quantified the cell viability within this thing, and here the fibroblasts are actually fibroblasts are marked with green color, and the keratocytes is the red color. So you can clearly see the fibroblast is present in the bottom, and the keratocytes present on the top. So this because this is the anatomical location of this cell types, the skin, and accordingly they could able to print this. So that's why this technology is very powerful to generate this kind of cell structure within the bioprinted structures. Now then they have studied this in detail on the in a mural model, where they have created the wound, and then that wound was actually then the same process, like that wound was first scanned with the Handheld scanner, and then the required amount of fibroblasts and keratocyte cells were printed on top on this within the thing. But after scanning, then CAD model formation, then actually giving commands to the bioprinter to print the required amount of dermis and required amount of epidermis, and those things are done. And then they have observed this over 6 weeks, how this wound model is regenerated, or the tissue regeneration or wound healing happens. Now if you see 1 week after this thing, now here they have used 3 steps, like the printing that we have discussed, the printing, how that in situ bioprinting, They have also used a matrix where no cells were used, only matrix materials have been printed. Suppose. And in another case, untreated, where the wound is created but no treatment was given. So that is no cells were printed or no in situ bioprinting was done. Then what they have done, they found that at 1 week, if you clearly see this, at 1 week the wound is fully closed or this epithelium is completely regenerated in case of printed, but in other cases there are still some area where epithelium is not fully regenerated, right? So wound closure is perfect in 1 week. And if you see further, in 3 weeks the wound is almost healed. But in this case, your wound closure completely, the wound is closed and the wound is healing. But in matrix and in untreated, still some amount of wound is left. So we can clearly see the wound, that part of wound is not treated. So still, so the because this wound is not getting is not closed in 3 weeks, so this can lead to different several complications like the infection or other things can be possible because of this the wound is not properly closed here. Then the wound is getting healed over time, and if you see here in week 5 you can clearly see this, though in both matrix and untreated the wound is healed, but the wound is also get contracted. But here there's very less sign of contraction, but in case of matrix and untreated there's large sign of contraction, as you see. And 6 was also the same thing is prominent here. The wound is completely closed, but less contraction here. The contraction is more. So in situ bioprinting helps in three things we can clearly see here: better epithelialization, better wound closure, and less contraction and faster healing. So these all four phenomena can be clearly seen, and this in case of in situ bioprinting, that is typically that is much better than the earlier, much better than the other two. Then they have also done a gross examination of the printed skin in a mural full thickness excisional wound model, where they have created this wound model by testing on the wound on the mural model on the mice on the skin. What they have done, see this thing, you see the wound closure that we have seen the gross examination, we have seen the this thing that this gross examination also, so we have seen now this from there they have also quantified this thing like the wound size. If you see here, no treatment, matrix, and then the printed. Clearly, at 1 week time, in case of printed, the wound size is lesser than the other two. Again, the size is getting reduced over time for all the groups, but for printed, the size closure is much faster than the other two. And by 3 weeks, the wound is almost completed for printed, but by 5 weeks, the wound is completely closed for other two groups. So it took 5 weeks for wound closure, but in case of printed, it is within 3 days, 3 weeks, the wound is completed. Then the healing was done for all the things, as we have seen in the earlier slide also. For 6 weeks, everything was healed. But again, if we see now that the microscopic images of that healed wound, then we see a marked difference between them, the groups. Like if you see here, so then also because they have used human cells on the model wound mice murine wound model, so that's why the human nuclear antigen can identify the human cells by this way. You can see the human cells are present on the mice. That's a interesting observation. The human cells are present and they can express, and then they are actually helping to heal the wound and also close out the wound. The Mason trichome stain typically gives us idea about the three things. First thing, we can identify the cell nucleus, we can identify the matrix also, and also we can identify the collagen fibers, because the collagen fibers here can be seen as blue stain. So here if you see, in case of printed week 1, the things are there, the wound is getting closed. In case of matrix, the wound is also there, and also, but still here epithelium is not fully established in all of these. Okay, and some amount of this thing is there. By week 3, in case of printed, epithelium is regenerated, but in matrix and untreated, the epithelium, there is no sign of epithelium. Also, you can see some Collagen fibers are also aligned within this matrix, but in this case, there is no proper alignment of these fibers that is visible. Then by week 6, epithelium is fully regenerated in most all the groups, but the tissue regeneration is much better in case of week 6, because if see the epithelium is the collagen fibers are aligned, they are perfectly ordered, but in this case collagen fibers, they are no perfect order is called collagen fibers can be seen. So a full thickness skin where we have bioprinted on the full thickness skin, then that can be instead of bioprinted on the full thickness wound, and then that can heal faster with this bioprinting thing. Again, I'm sorry for this. This slide contains a lot of data, but yeah, this is also very important images for this thing. Again, they have actually gone to the higher animal, like the porcine model. They have chosen for to understand the this wound healing with in situ bioprinting methods. Like what they have done, this A is the image of the wound healing in situ bioprint, autologous and allogenic fibroblast and keratinocytes. So here they have used both autologous. Autologous means where this cells are isolated from the murine model portion from the same pig, and then that is used. Allogenic means this it is from the other pigs, okay, and only matrix was used and untreated where no treatment was given. Matrix only, in the matrix only fibrinogen and collagen was used as a matrix, and up to over 8 weeks they have studied the whole thing. And if you clearly see here, in case of formation of epidermis island at the core of the autologous treatment started as early as week 2, and complete wound closure and epitheliation with minimal contracture was achieved by week 4 of the study. All the treatments appear to contract significantly with little epithelium forming primarily from the edges of the wound. In most of the cases, like if you see, the epithelium regeneration is not even started, but in case of autologous, the epithelium regeneration started as early as week 2, and complete wound closure happens in week 4. Complete wound closure happen, but in other cases, this is not typically does not happen. And then by 8 weeks, this wound completely healed. In case of autologous, allogenic also the wound healed. There is some amount of still left, but in case of matrix, there is a large contraction, and also in case of untreated, there is a large contraction can be clearly visible here, right? So this study, the murine model, they have studied the in situ bioprinting. If you see a large wound was created, and then that could heal with in situ bioprinting, that could heal faster, like within 8 weeks, complete healing was observed, and less contraction than the other three methods. Then in B, you see significantly smaller open wound size was measured for autologous cell treated wounds compared to the other treatment. For autologous, for autologous, a like the a faster wound healing is possible because of for this autologous, and for other groups, the wound healing was not that thing was not that great, right? And also in C, the wound contraction was reduced for in autologous cell treated wound compared to other. Here also, if you clearly see here, the autologous, the wound contraction is much lesser than the other group, other things, right? The other group, the wound contraction is much higher, and in case of this thing, the wound contraction was much lower. And also in case of autologous cell treated, so as we have seen that the wound contraction is much lesser in this autologous group than the other three group. So that also helps for very faster. That also helps in faster tissue regeneration without less contraction. And also the autologous cell treated wound showed significantly accelerated reepitheliation compared to the other groups. That is also another important observation from this study, that where the autologous in the autologous cell treated wound so significantly accelerated reepitheliation and compared to the other groups. Right here, as you can see here, the autologous group, as early as in 2 weeks, 80% of the epitheliation done, and for other groups it took much longer than the this thing. So this study has some important observations. From this study, some important observation is like, again, earlier faster reepitheliation, faster wound contraction, no, not wound, sorry, faster wound closure, better reepitheliation, and less wound contraction. That is possible because in case of in situ bioprinting, and that too when autologous cells are used, that helps in definitely better, faster tissue regeneration. Also, they have also done some macroscopic observation examination with the of the H&E stent. You can clearly see here, in case of untreated matrix allogenic not autologous. In this case, week 2, here the epithelium is restored almost, but in allogenic matrix and this is not yet done. In week 4, in this allogenic and this case is the epitheliation done, but in this case some epitheliation, very small epitheliation is done, is started, and by week 6 in most of the groups, all the groups probably, epitheliation is done and this is present. Also, by week 4, autologous bioprinting node showed formation of retipig epithelial projections into the dermis. This epithelial projection that is present typically, this epithelial cells, epithelial tissue is getting, is like this kind of undulating surface or wavy features. This is typically present in the skin, that is getting established in case of autologous thing, that is getting present. And when treated with bioprinted autologous cells showed early formation of loosely organized capillary layer above the denser, thicker layer of epidermis. This is clearly saying this wound treated with bioprinted autologous cells showed early formation of loosely organized papillary layer above the denser, thicker layer reticular dermis. This papillary layer that is also clearly visible here. The structure of the tissue appeared mature and complete at 8 weeks with nicely woven dermal collagen here, and regularly distributed vasculature also can be clearly seen here. So this study, so this from this slides, the microscopic examination of the H&E stent sections clearly showed us again same thing like the earlier epitheliation, and then epithelial this retipig epithelial projections within this tissue, and also loosely organized papillary layers above the denser, thicker layer of reticular dermis, and also the nicely woven collagen architecture and the regularly distributed vasculature within this thing. So this, in this case, in case of autologous in situ bioprinting, the autologous cells give provide better tissue regeneration. Also, that is very good for this, good for the bioprinted for better tissue regeneration. Now, this study, like this in this study, their main purpose is to use this technology directly on the patient wound bed when there is a large amount of skin getting defected, like people coming back from work, they have large wounds where some part of skin, muscle, bone can get damaged. So suppose, but this in this study they are mostly concentrating on the regenerating of the skin tissue, where but this technique can definitely, this technique can, because for generating large wound there are very less strategies or clinically approved strategies are available, and if we can do that, that can be very helpful, and that can save the patient, because many patients they die because of the large wounds, because that wound that can get infected fast and infected. If the wound is not properly closed, then they can get infected, and also there are other challenges. So with in situ bioprinting of this kind of skin graft, we can close the wound faster, as we have seen here. Within 2 weeks, the wound is complete. The wound is getting closed. So that's a very good, that's a very good outcome of this study, and they definitely this kind of thing. So in Wake Forest Institute of Regenerative Medicine, they are targeting the wound. Sorry, they are targeting the war veterans who are coming back from war, and when they have large this kind of wounds, so that this technology can be very well used to directly print with their own cells, like the autologous cells can be collected from those from those patients, and then that can be used for in situ bioprinting of the skin construct directly on their wound bed, and then to that can help in healing this wound much faster. Thank you very much for attending this lecture. So we'll see more in the next week. Thank you.